So we finished up the bipolar junction transistor. Those are the NPNs and PNPs transistors that have their PN junctions back to back with a base in the middle, an emitter, and a collector on both ends. Okay, but the science of making that PN junction involves diffusion. Okay, basically, what diffusion is normally is think of in terms of gases. If you've got two different gases separated, okay, and you open up a window between them so that one can pass into the other, the diffusion process actually is at work where one gas mixes up in with the other gas, so you get a well-mixed mixture of gases. And it takes time for the mixture to develop until it's a homogeneous thing. Well, the same thing can be done in the solid state, but of course we don't have the solid state. We're dealing with solids, not gases, so it takes time for one element to diffuse into the body of a totally different material. So, in other words, how do you get the phosphorus to diffuse into the silicon? Okay, that can be, you can figure out mathematically how it happens, and what happens is as that phosphorus or whatever the dopant diffuses into the silicon, okay, you create a concentration gradient. What that means is it's not a constant concentration of phosphorus in silicon. It gradually decreases as the depth from the surface of the silicon. All right, so in building a proper PN junction, okay, in many of the devices, you're involved with using diffusion. You diffuse material into the silicon or the germanium, but mainly we use silicon. And it takes time. And you want to develop it so a particular concentration is there at a specific depth, the depth of which is where you create your PN junction. All right, and so the process itself involves, first of all, deposit of a dopant material. Okay, then you have to heat it up, and heating up, depending on what temperature it is, and depending on what the concentration at the surface, the dopant concentration at the surface is, in time you get a gradual diffusion into the body of the silicon. All right, and you wait, and at a specific time to which you will have just the proper concentration at the PN junction to get you the properties that you want. Okay, and those properties basically is your depletion region, or your depletion region. So a lot depends on what happens in the depletion region, both as a bipolar junction transistor, where you have a forward bias condition, which shrinks the junction, or reverse bias condition, where the junction itself, the width of the junction spreads out, gets wider. Okay, that's the bipolar junction transistor. The other thing about the bipolar junction transistor is that basically it can operate as a switch. As a switch. Why would you want it to operate as a switch? Well, because today's circuits are binary circuits. Binary circuits mean that they have two states. Electricity has two states, as a 0 state or a 1 state. That's binary, 0 or a 1. Okay, so in the case of a transistor, a bipolar junction transistor, we can choose the 0 state being when it's closed, when the switch is closed. You have nothing traveling through the transistor, no current. However, when you turn the transistor on, such as creating the right conditions for, such as a current to a base, which will open up which will actually close the switch, and now you get a current going from the emitter to the collector, and that's a closed state, and that gives you a 1. So you have the options of creating a conducting or non-conducting, okay? The bipolar junction transistor, though, operates on a current. In other words, the current decides whether it's on or off, okay? A few years after they've developed the bipolar junction transistor, somebody got the bright idea is instead of using conduction through the P and the N and the P, or the N, the P, and the N, instead of doing it that way, why not create a condition where you create a channel, a conductive channel. Okay, now that channel can be an N-type conduction or it can be a P-type conduction. Does it conduct by electrons or does it conduct by holes? Okay, and that is the invention of the field effect transistor. Why is it a field effect transistor? Because you're adding a voltage, and basically it operates on the basis of creating a voltage. A voltage is created so that you either open or close a channel for the current to flow in. So the FET, field effect transistor, works on the basis of a voltage. So voltage is control. Now, they're usually called metal oxide semiconductors because that's how they're made. You have a metal on top of an oxide, which is a insulating material, and the semiconductor is right under the oxide itself. So on the metal, you create a potential on the metal, and that potential creates an electric field across the insulator that affects then what the thickness of the channel is in a field effect transistor. This is what we're going to learn today. So there are lots of differences between the bipolar junction transistor and the field effect transistors, and I'm sending you a table in today's lesson that goes through all the different ways that they're different. Okay, but for your purposes, just remember the ones that are highlighted in yellow. Okay, those are the important factors between bipolar junction transistor, field effect transistors. The nice part of the field effect transistor, or the MOS, it's actually CMOS that's used, is that that's the kind of transistor that is used to build most of your integrated circuits. We rarely use the bipolar junction transistor. We use the metal oxide semiconductor transistor to perform a lot of the functions that the integrated circuit needs to do. And the integrated circuit, it operates as a binary circuit. Okay. So let's get going, and we'll first discuss field effect transistor. Okay. And if any questions, call me up or ask me questions. I can write something special on you. for you and share it with everybody else.